record option. Okay, let's just take a picture. Okay, cool. Let me try that then. Can you guys see my screen? Okay. And then it's coming out in the recording, right? Okay, cool. Awesome. Okay. Finally. I'm so sorry about that, you guys. I think we should be good to go now. Let's see. Yeah. If you all know people who are trying to join through, just go ahead and tell them to come through Discord, because yeah, that seems to be the way we're gonna have to do it tonight. But I'll go ahead and get started here in about 2 minutes. Yeah, so we're recording this basically Discord call with Microsoft Teams, and so we'll upload that recording to YouTube. Yeah. I'll give it a bit. Okay. I'm gonna go ahead and get started now. But yeah, just tell your classmates, and I guess I'll do the same too in the Discord. But yeah, this is being recorded, so we'll upload this to YouTube once we finish here. But yeah, okay. So we'll go ahead and get started. For y'all's exam 1, y'all are doing an entire exam on strictly time domain. So there is a lot to cover. I'm really gonna try not to go over 2 hours, but there's a lot, so bear with me. If you have to leave at any moment, just remember this is being recorded, so you won't miss anything. But yeah, so to start off, these first 3 topics, complex numbers to discrete time signals and discrete time systems, these are just going to be, I'm going to try to go through them quickly, but they're going to be the foundation of this course. So we need to really make sure that y'all understand this for the test. I'm going to go over some concepts, some things you should know that are going to be really useful for the test. And then once we basically have a good foundation of these 3 things, then we can go into a lot of examples here with solving DT-LTI systems, one using difference equations and convolution. So we'll do lots of examples here. But yeah, we'll go ahead and basically just get started now. But like I said, this first 3 is really important that you understand it. It's going to help you with the rest of the course. But yeah, so really quickly, the complex number review. So this should be review, so it should be simple, but I'm just going to go through it really quickly. So we can have a complex number z, okay, and it's equal to x plus jy. That's called rectangular form, right? And then we can also represent it in polar form, where we have z is equal to the magnitude of z times e to the j of some phase angle. So this is called polar coordinates. Okay. And the way these are related is we can have x is equal to the magnitude of z times cosine theta. Y is equal to the magnitude of z times sine theta. The magnitude of z is equal to the square root of x squared plus y squared. And theta is equal to the arc or tangent inverse of y over x. Okay, so in this class, you're going to be messing a lot with complex numbers, so you want to be sure you know these to heart really well. And then, of course, the probably most important identity that you guys should know is going to be Euler's formula. So e to the j theta is equal to cosine theta plus j sine theta. Okay, and a more general form of that is if we have z is equal to the magnitude of z times e to the j theta, then we can also say that it's equal to the magnitude of z times cosine theta plus the magnitude of z times j sine theta. Okay, and then lastly, can you hear me? Okay, yeah, my Wi-Fi is really not too great right now, so let me just connect to my hotspot. I'm just gonna do that from now on. That way it doesn't disconnect again. Where you at? Okay. All right. Let's hope this goes smoothly now. All right, y'all can see my screen? Okay, cool. So yeah, what I was saying is that this identity right here, cosine theta is equal to e to the j theta plus e to the minus j theta over 2 is very important to remember, as is sine theta is equal to the e to the j theta minus e to the minus j theta. Hold on. Okay. Minus j theta over 2j. Okay, that should be all right. Jeez. Let's see. Okay. Is the screen sharing now on Teams, Hansby? Okay, cool. All right, we should be good now. Okay, so this is just a quick review of complex numbers. This is stuff that's going to be used all the time in this class, so just make sure y'all take these identities and just remember them to heart. Okay. Moving on to discrete time signals. Okay, so we're going to cover a few things. We're going to cover some functions y'all should know, signal notation, and some transformations. I'm going to try to go through that really quickly. Okay, so for some discrete time signals, let's go over some discrete time functions that are going to be really important to this class. Okay. So the first one is going to be the delta function. Okay. And this delta function is just notated by this lowercase delta. Okay. All it states, delta of n is equal to 1 whenever n is equal to 0 and 0 otherwise. Okay. So if we look at that on a graph, it's pretty simple. We have x of n here and there. We have 0 here, 1, 2, 3, minus 1, and continues. X of n is only 1 at n is equal to 0, and it's 0 everywhere else. Okay. Some other names for this function, it can be called the impulse, or it can also be called the unit sample. Okay. Another function is called the step function. Okay. And this one's denoted by u of n. Okay. So u of n, can y'all see my screen? Oh my god. Okay. Okay, hopefully it should be good now. Jeez. Okay. Everyone can see my screen, right? Is it loading now? Okay, can everyone see my screen now? Is it loading for everyone? All right, don't get AT&T, y'all. Let me try resharing. Okay, try now. Y'all can see it now? Y'all, yeah. Y'all are able to see the screen, right? Okay, cool. Okay. Hopefully no more problems. Okay. The step function is simply defined as 1 when n is greater than or equal to 0, and 0 when n is less than 0. So the way that looks when we actually graph it as a signal is simply at 0 and all the way to infinity, we just have a 1 everywhere, okay? And that continues on forever, okay? And everywhere below 0, it's just 0, okay? So that's the step function. The other really important function is our exponential function. Okay, and this one is just defined as x of n is equal to p to the n times u of n. Okay, and p can be real or it can be complex. But I don't think y'all seen it for the case that it's complex yet. I don't think you'll really see that till the frequency domain. For now, it's really just real. But when it is complex, it just looks like this. But for this case, I think since y'all are just seeing it real, an example of what an exponential function would look like is simply x of n is equal to 1/2 to the n. So in this case, p is equal to 1/2 times u of n. So what that would look like is just a decaying exponential. So at n is equal to 0, we have 1/2 to the 0 is just 1. We got a 1 here. 1/2 to the 1 is 1/2. Okay. 2, we get 1/4. 3, 1/8. 4, 1/16, and so forth. It's a decaying exponential. Okay. And when you multiply any function times this unit step function u of n, it basically makes it to where it only starts at n equals 0. Every value of x of n where n is less than 0 is always just going to be 0. Okay. And the last function that you'll see a lot is the sinusoid function. Okay. Its general form is x of n is equal to a times cosine omega naught n plus theta. Okay. And here a is simply your amplitude of your sinusoid. Okay. Omega naught is your fundamental frequency. Okay, so that's just the frequency at which the sinusoid oscillates. Okay. Theta is the phase of the sinusoid, so how much phase it's been shifted by. And this isn't in the general form, but it's good to know. N naught is your fundamental period. So how long it takes for the sinusoid to repeat. And N naught is simply equal to 2 pi over omega naught. Okay. Okay. And what this looks like is just like any other sinusoid in continuous time, except it's little stem plots. And so forth. And you can kind of see the sinusoid there. Okay. And one thing I forgot to mention that should have been before I guess I went over these important signals is signal notation. Okay. We can have a stem plot, which is what I've been drawing. Okay. So at -1, let's say I have 3. Let's say I have 2 here at 0. At 1, I have 0. At 2, I have -3. And then I have 1 here at 3 and 0 at 4. Okay. So this is one representation of signals. It's an actual visual representation of it. You just plot little stems for each discrete value of n. And this is just called a stem plot. Okay. Another way is bracket notation, which is what you'll use a lot, where x of n is simply equal to, and what you'll do is kind of just list all the values of n in sequential order that are important. So for this case, we would say 3, 2, 0, -3, and then 1. And the underline dictates where n is equal to 0. Okay, so this is for n is equal to -1, n is equal to 0 here, n is equal to 1, n is equal to 2, n is equal to 3. And with this bracket notation, it's assumed that if it's not listed within this bracket, for all other values of n, x of n is simply equal to 0. Okay. And if y'all have any questions, just feel free to interrupt. Okay. So next is signal transformations. Okay. The first transformation I'm going to talk about really quickly is just amplitude transformation. Okay. And this one's quite simple. So if I have this function, x of n, I'm going to draw it out. So at n is equal to 0, I've got a 2. At n is equal to 1, x of n is equal to 1. At 2, we'll have 3. And at 3, we'll have another 1. Okay. And so everywhere else, if I just want to keep going, is 0. Okay. If I say some other function w of n is equal to 2 times x of n, this 2 is the amplitude transformation. It means we're taking x of n and multiplying it by 2. And so all that would be is you literally take all the values and multiply by 2. So at n is equal to 0, we've got 4 instead of 2. At n equal 1, we've got 2. N equal 2, now we've got 6. And at n equal 3, now we have 2. So this is 2x of n. Okay. The next one, which is probably the most important one, which you'll see a lot, is time shifting. Okay. So if we have that same x of n, and we want to say another function w of n is equal to x of n minus 3. Okay, this is a time shift. This just means we're going to shift the whole signal to the right by 3. So what that would be is instead of starting at n is equal to 0, we're going to move over 3 places. So we'll start at n equals 3, and that's where our first x of n will be at 2. And then we'll keep going, just finish out the graph. We got 1 right here. At 5, we'll have 3. Okay, and then at 6, we'll have 1 again. Okay, so that's x of n minus 3. We simply shift over the graph by 3 spaces. Okay. The other one, we can say z of n is equal to x of n plus 3. Okay, so this is the same thing except we'll shift left by 3. Okay, so always just remember opposite. If you see a minus in the braces, that means you're shifting right. If you see a plus, it means you're shifting left. Okay, let me actually move this axis since we're going to go negative. Okay, so 0 is right here. We'll have -1, -2, -3, -4, -5. Okay. So we'll shift the whole thing over. So instead of starting at n is equal to 0, we'll start at n is equal to -3. So the 2 goes right here. The 1 goes right here. The 3 here. And the last one here. Okay. So where the previous places were originally, they're now 0. Okay. So that's time shifting. The other thing is time reversal. Okay. So time reversal is just simply, we have our same x of n. Okay. I'll redraw it. At 0, we had 2. At 1, we had 1. 2, we had 3. And at 3, we had another 1. Okay. If I have x of minus n, all that means is we are going to flip the original signal about the y-axis. Okay. So what it's going to look like is you literally just flip it over the y-axis. So this 2 is going to stay here at 0. Okay. But now at -1, we'll have 1. At -2, we'll have 3. And at -3, we'll have another 1. Okay. So we legit just flip over the signal. Flip the signal over the y-axis. That's all time reversal is. Okay. And the last thing is it's not really a signal transformation, but it's definitely something you should know for this class, and I'll just call it functions expressed as delayed impulses.
Hey, what about times?
There's that too. If y'all want to study that, y'all can, but I can tell you from experience, it's probably not gonna be on the test. The only time you'll really see that is that when you were really studying it for that one quiz. But you won't usually see time scaling because it'll actually disrupt like your discrete intervals. More often than not, you're just going to see time shifting, amplitude transformation, and even time reversal is very scarce. The reason I'm showing y'all time reversal is to kind of get more of an intuitive understanding of graphical convolution once we get there. But really, the two important ones are going to be time shifting and amplitude transformation. But yeah, so functions expressed as delayed impulses. So I'm going to draw the x of n that we've been using. Okay. So at 0, we've got 2. At n equals 1, we have 1. N equals 2, we have 3. And n equals 3, we have 1. Okay. If I write this in bracket notation, it's simply 2 with the underline because that's where n is equal to 0. Right? And then 1, 3, and then 1. Okay. One thing that's really cool about the delta function, and also another reason it's called the unit sample, is it literally samples a screen capture of a signal, basically. So if I say x of n times delta n, I'm multiplying it by the delta function. What that's doing is at n is equal to 0, the delta function is 1, right? And at n equals 0, our signal x of n is equal to 2. So if I multiply by the delta function, it's literally sampling this one part of the signal right here at n is equal to 0. So if I do x of n times delta n minus 1, okay, so I'm time shifting delta n minus 1. I'm just shifting it over to the right one, so that's simply, if I've got 0 here and here, now the delta function is right here at n is equal to 1. Okay. So here, when n is equal to 1, I've got x of 0 times delta of 0. Okay. So that'll be 1 times 1, and we get 1. So that's just sampling this part right here. And we can do that so forth. So x of n times delta n minus 2. If we multiply by a delayed delta by 2 time units, we'll go ahead and sample this part of the signal. Okay? And what I'm getting at with here is that basically any function can be represented as a summation of delayed deltas. So basically, I would just have x of n is equal to 2 delta n, okay, plus delta n minus 1 plus 3 delta n minus 2, and then plus delta n minus 3. Okay. And these are our actual values of x of n. So in this case, it's 1, 3, and then 1. And these delta functions are 0 except when the inside condition is equal to 0. So at n is equal to 0, we'll go ahead and extract that 2 for x of n. At n is equal to 1, we'll extract that 1. At n is equal to 2, we'll extract that 3. And at n is equal to 3, we'll extract that 1. And so when we sum them all together, it gives us the entire picture of x of n. Okay? Hopefully that makes sense. Any questions so far? No? Okay, cool. Then we'll go ahead and move on. So let's do an example really quickly. Hold on real quick. Let me get my page. Okay, so we're just going to do a quick example to kind of summarize what we've been messing with signals. Once we finish that example, then we'll move on to systems. Basically, let's do this example. We're going to say plot x of n is equal to u of n plus 2 minus 2u of n plus u of n minus 4. Okay, so I think the best way to usually go about this is to kind of graph them individually. So for u of n plus 2, let's simply remember the step function is just a bunch of ones starting at n is equal to 0 and continuing on to infinity. But if we time shift it by 2 to the left, because we have that plus sign, well then instead of starting at 0, we're going to start at negative 2. So our step is starting at negative 2, and it'll continue on towards infinity. Okay. Here and ignore the signs for now. We'll come back to those. So if we're just looking at 2u of n, okay. Well, then we've got the regular step function starting at 0, but it's being multiplied by 2. So instead of 1, we'll just have 2. And that'll repeat towards infinity. And then lastly, u of n minus 4. That's just the standard step function, except time shift it to the right by 4 units. So we'll start at n is equal to 4. And then continue that on to infinity. Okay? And so now looking at this together, we have this as positive, we're subtracting this function, and then we're adding this function. So if we just take this case really quickly, if we have these 1s and we're subtracting these 2s, well, these 2s don't come in till n is equal to 0. Everything before n is equal to 0 is equal to 0. So these two little stem plots right here at n is equal to -2 and n is equal to -1, they don't get touched at all. So we'll draw them here. That's at -2 and -1. Okay. But starting here at 0, now we're going to have 1 minus 2. So that's -1, right? So we'll keep doing that. So it's -1, -1 at 2, -1 at 3, -1. Okay. But once we get to n is equal to 4, now we also have to take into account this step function. Okay. So now we've got 1 minus 2, which is -1, but then we're going to add the 1 starting at n is equal to 4, and that's going to continue to infinity. So from n is equal to 4 on out, we're always going to have 1 minus 2 plus 1, which is just equal to 0. So that means everything else after 3 is 0. So this would be our result when we plot it. And if we want to put it in bracket notation, it's simply x of n is equal to 1, 1, minus 1 at n is equal to 0, minus 1, minus 1, minus 1. Okay. Any questions on that? Okay. So now moving on to systems. Okay. This is where the class really picks up, I would say. So that was signals. Okay, so that's one part of the class. The second part is systems. So system is simply defined as a device or process that accepts an input signal. Okay. And in our case, in discrete time, we're calling our input signal x of n. Okay. And produces an output signal. And for the purposes of this class, we call that output signal y of n. Okay. So if you want to look at that visually, you have an input signal x of n. Okay. We put it through some system, and we get an output signal y of n. Okay. And these signals can be anything. So like this could be like music on a guitar, like you're just playing your guitar. Okay. And the system itself could be an amp. Okay. And the output signal you get is the amplified guitar sound. Okay. Now, in this case, that wouldn't necessarily be completely true because, I mean, I guess if you're using a digital guitar or something, but either way, that kind of sums up what a system is. You just put any kind of input signal, so like a guitar sound, put it through a system, such as an amplifier, and that system is simply going to do some kind of modulation and transformation. It's going to change that input signal in some way and produce that changed signal as an output signal y of n. Okay? And the way we basically represent these systems is through what's called difference equations. Okay? And difference equations are simply just a mathematical model for representing discrete time systems. Okay. And one thing that always helped me is like if you think about it in continuous time, all systems are represented by differential equations. Okay. But in discrete time, which is what you're messing with in this class, instead of differential equations, systems are simply modeled by difference equations, which honestly makes our life a lot easier because I would rather mess with difference equations than differential equations. But okay. And then I'm sure y'all seen this in class before. And the first time you see it, it's fairly intimidating. But I want to try to clear up some fog around this. So let me just draw it out and then I'll explain it. Yeah, when I took the class, I thought he was writing H, but nah, it's K. It doesn't matter as long as you stay consistent with it. But so what this is right here, this formula, it's just the general form of a linear constant coefficient difference equation. Okay. And the thing with this class is it's very important to kind of connect the math to the visual aid. Since this class gets very math heavy, it's sometimes hard to kind of remember and relate that, okay, you're messing with signals and systems. You see a lot of equations and you kind of forget that, okay, this could be an actual real life signal or something. And this general form of a difference equation, all you got to remember is just that it's describing the system. Okay, it's just the mathematical way of describing a system. It tells you what it's actually doing to that input signal and how it's going to produce an output signal. Okay, and this part right here, I'll do that. This first summation is simply the previous output terms. Okay, and so if a system is kind of dependent on previous output terms, you can think of it as having feedback. Okay, it produces an output signal based off the previous outputs itself. And this summation right here is the present and previous input terms. Okay, and I'm just going to write an example of a difference equation real quick and to kind of show you how this summation, this general form relates to equations you'll see in problems. So if I have a system that's represented by this difference equation, y of n is equal to 3 y of n minus 1 minus 0.5 y of n minus 2 plus x of n plus 2x of n minus 1, okay? So you'll see stuff like this a lot in this class, I imagine, right? And remember, this difference equation is simply describing the system. It's telling us that the output signal we're going to get from that system is doing all these mathematical things, okay? It's taking the input signal, it's taking the previous input signal, it's multiplying that by 2, it's taking the previous output signal, multiplying that by 3, taking the previous signal from 2 timestamps ago, multiplying it by half, and it's summing all of those up, okay? This is just describing the behavior of the system, what it's going to do to our input signal to produce this output signal, okay? And so the way this relates to this general form of a difference equation is if we look here, let's first look at these output terms, the y's, okay? We've got this summation from k is equal to 1 to n. In this case, n is equal to 2, okay? So here we've got n minus k. So we got little n minus 1, little n minus 2. Okay, so that summation would be from k is equal to 1 to n is equal to 2. Okay, so that means this 3 right here is a sub 1, and the 0.5 right here is a sub 2. Okay, remember we're relating it to this summation right here. In terms of the inputs, okay, L, so the top limit of the second summation, is equal to 1, okay, because our highest value of k is just 1 and minus 1. Okay, so this would be, if we look back at the input terms, this would be for k is equal to 1, this would be for k is equal to 2. For the input terms, we've got k is equal to 0, k is equal to 1. And in this case, b sub 0 is equal to 1, and b sub 1 is equal to 2. Okay? So that's how this general form kind of relates to difference equations you'll see in class a lot. I just wanted to try to clear that up because I know the first time I saw this general form, it was like, I don't know what I'm looking at. And the reason we start this summation limit for the output terms at 1 instead of 0 like we do for the input terms is because we've kind of already taken the k is equal to 0, which would account for y of n, and just moved it over to the other side right here. Okay. Let's see. Yeah, so if we were to kind of rewrite this difference equation in the form of a summation, we would basically have y of n is equal to the sum of k is equal to 1 to 2 of a sub k y of n minus k plus the summation of k is equal to 0 to 1 b sub k x of n minus k. Okay, and if we expand this summation out and actually put them together, a sub 1 is simply 3, which accounts for y of n minus 1 at k is equal to 1. K is equal to 2. We've got a sub 2 is negative 0.5. Okay, and that's for y of n minus 2. And we come over here at k is equal to 0. We've got b sub 0, which is just 1, which accounts for x of n. And at k equals 1, we've got b sub 1 is 2, which accounts for x of n minus 1. Okay, so those are difference equations, and I hope that kind of cleared some confusion up about what we're actually messing with when we look at these equations. And these are just, remember, they're just describing systems. Okay, mathematical definition of a system. Yeah. So now, all of the systems that we'll be messing with in this class are called discrete time linear time invariant systems. Okay. The reason we mess with these systems is, in nature, a lot of systems are kind of naturally occurring linearly and time invariant. But these linear and time invariant systems have some really cool properties that we can manipulate when trying to basically solve the system. So for one is that linear property. Okay, the linear property simply means that the system is scalable, and I don't think this is a word, but I'm pretty sure y'all get what I mean. Addable. Okay. So all that means is, for the scalable part, if we have some function x of n, we put it through a system, and we get some signal y of n, okay? If we multiply that same signal, that same input signal, by constant c, and we put it through a DT-LTI system, we should get that same output also scaled by c, okay? And the add part is simply, if we have a signal x1 of n, put it through a system, and we get another signal y of n, y1 of n, and we have another signal x2 of n, put it through a system, and we get an output y2 of n. Okay. If we add those two input signals together, and we put the summation of those two signals through the same system, we should get the sum of their individual outputs. Okay, so that's linear. And you can combine these properties just like a linear combination. So if I have a constant alpha times x1 of n plus a constant beta, beta x2 of n, I put it through a system, then I should get alpha times y1 of n plus beta times y2 of n. And one thing real quick I forgot to mention when it comes to this difference equation is I said it's linear, which is correct. We're messing with linear systems, and it's constant coefficients. So these a sub k's and these b sub k's are always going to be constant coefficients. Okay, there's never going to be a coefficient a sub k that is a function of another variable. They're always going to be constants. Okay. And of course, the other property of LTI systems is time invariance. Okay. So time invariance simply means if an input signal is shifted by a certain amount, so too is its output. Okay. So what that means visually is if we have x of n, put it through a DT-LTI system, and we get y of n out. Okay. If we shift x of n by some k, okay, and put it through the same system, well, then we should get that same output that we got before, but shifted by the same amount as well. Okay. So one kind of way of looking at that is if I have like simply an impulse, okay, that's my x of n. I put it through a system, a DT-LTI system, and the signal I get out is this decaying exponential, okay? And this is simply 1/2 n u of n. Okay, if that's what I get, if I put some impulse through a system and this is the output signal I get out, well, if I go ahead and shift that impulse, and this is going to demonstrate both the time invariance and linear properties, if I multiply that impulse by 2 and I also shift it by 1, what I get is 0, 1. I'm shifting it over to the right by 1, right? But I'm also multiplying it by 2. Okay, so that's my new input. I put it through the same system, and what linear time invariance tells me is that I should get this exact same output signal, like the general shape of it, but transformed in the same way that the input was transformed. So the input was shifted over by 1. So instead of starting at 0, this output is also going to start at 1, just like the input was. And just like the input was multiplied by 2, so 2 is the output. So instead of the first term being 1, we're going to have 2. Instead of the second term being 1/2, we'll have 1. And then we'll have 1/2. And then 1/4. And so forth. Okay? So this would be 2y of n minus 1. Okay? And so these linear and time invariant properties are very important to solving systems. We're going to be taking advantage of those properties quite a bit to basically develop methods to determine the output signal of a system. Okay, this convolution literally takes advantage of all of these, and I'll explain that once we get there. But for now, we're going to go ahead, and that should cover basically most of the groundwork. Now we're going to get into actually solving some difference equations. Okay. So when we're solving a DT-LTI system, all we're doing is if we're given some input signal, Okay, this is given. We're also given a system represented by a difference equation, okay? We want to determine what that system is going to produce when excited by this input, okay? That's literally the whole purpose of this class. You're going to be determining different methods to solve this problem. When given an input signal and given the representation of a system, how do we determine its output, okay? So the first method y'all learn is using difference equations and using the characteristic and particular solutions, kind of like y'all did in differential equations, right? So the first thing we have is the particular solution yp of n. Okay. And what the particular solution is simply the response of a system, and that response is our output y of n, caused by a specific input signal, which we call x of n. Okay. The second type of solution y'all came to know was the characteristic solution, right? Yc of n. Okay. And what the characteristic solution is the natural response of a system. Okay. When there is no inputs. Okay. So there's zero inputs to the system. What does the system naturally do when not excited by anything? That's the characteristic solution. Okay. And then your total solution. Okay. What output does the system produce is equal to the particular solution plus the characteristic solution. Okay. And this total solution is what's known as either the general solution or the total solution. Okay. So how do we go about finding the particular solution? Okay, because that's the first thing you'll be doing. How do we find yp of n? Okay, the way you do that is use the input to particular solution table that was given in your notes. That won't be given on your test, I imagine. So I think you'll have cheat sheets for the test. So just make sure to write that down. That table that kind of relates different classes of inputs to different particular solutions. But basically, you'll determine the general form of your particular solution based off that table. Okay. And once you figure that out, you'll go ahead and plug that general form yp of n back into the difference equation. Okay. And once you do that, you'll just simply solve for the constants. Okay. And that's how you find your particular solution. And we'll go through an example here in a bit once we get through characteristic solution, because all the examples make you solve for both of them. But the table you should have gotten should be this table, x of n, and then yp of n. Okay. And so when x of n is u of n, we'll simply have c1 u of n, or just simply c1 if we know for a fact that our system is causal. I guess I didn't talk about this yet, my bad, but a causal system is simply no output is generated before n equal to 0. Okay. So for n less than 0, that means that y of n is equal to 0. Okay. That's what a causal system is. And in this class, I believe you're only ever messing with causal systems. The other one is nu of n, okay? And you get C1 plus C2n for n greater than or equal to 0. Again, if it's not causal, then you need to make sure to include that u of n. But for this class, I don't think you need to worry about that because everything is causal. For a class of input where we have some constant raised to the n power times the step function, u of n, then we will get C1 a to the n for n greater than or equal to 0. Okay. For sine of n theta and cosine of n theta, we get the same particular solution, and that's this function C3 sine of n theta plus C4 cosine of n theta. And these namings of the constants don't matter too much. Just have them distinct. So if I wanted, I could have put 1 and 2 here. Just my notes have 3 and 4. I'm honestly not too sure why, but as long as they're distinct, because they are two different constants. Okay. And the last two classes of signals are a to the n cosine of n theta. And we will have C1 a to the n sine of n theta plus C2. And then a to the n sine of n theta. The particular solution we'll have is C1 a to the n cosine of n theta plus C2. Okay. So this right here is our particular solution table. Either memorize this or write it on your cheat sheet because this is really important. So yeah, when I refer to step 1, use this table. Just if your input is u of n, go ahead and basically your output particular solution is C1. Plug that C1 back into your difference equation and solve for C1. Okay, and we'll do an example of that here in a bit. Let's just get through the second part of solving a difference equation, and that is the characteristic solution. So how do we find y c of n? Okay. So the first thing we need to do is determine the characteristic equation. Okay. Once we've determined that equation, we need to find the characteristic roots of that equation. Okay. And these roots can either be real and distinct, real and repeated, or complex. Okay. And there's a different solution for each of those roots, which I'll write here in a bit. But basically, we'll plug those roots back in. We'll plug the roots into the general form of y c of n. Okay. Step 4, use your particular solution to come up with your full solution. So yp of n plus yc of n is equal to y of n. And at this point, you should still have constants. And so your last step is to use initial conditions if they're provided to find constants. But if they're not provided, the tip I have for you is use n is equal to 0 and n is equal to 1, because more often than not, you'll have either 1 or 2 roots. You'll rarely have 3 roots. But use n is equal to 0 and n is equal to 1, and plug that into your difference equation. And basically, that will give you your own set of initial conditions. Okay. Okay. And then for the characteristic solution, the characteristic equation is written in this form: AR squared plus BR plus C is equal to 0. It's just a quadratic. And this will determine R1 and R2, which are our characteristic roots. And this is our characteristic equation. Okay. And so if we have real distinct roots, then YC of n is equal to C1 times R1 raised to the n plus C2 times R2 raised to the n. Okay. If we have real repeated, then we will have YC of n is equal to C1 times R1 raised to the n. Well, I'll just call it R, since in this case R1 is equal to R2. Plus C2 times n, that's the difference, times R raised to the n. Okay? And then finally, complex roots. And the thing with complex roots is that R2 is equal to the conjugate of R1, and C2 is equal to the conjugate of C1. Okay? So your what's it called? Your roots are complex, but also so too are your constants. And they're both going to be complex conjugates of each other. So this form is YC of n is equal to C1 times R1 raised to the n plus C1 conjugate times R1 conjugate raised to the n. So when you have complex roots, it sucks because there's a lot of algebra, but it's worth it in the end, because once you have C1 and you have R1, you also have C2 and R2 because they're just complex conjugates of each other. Okay. So let's now go ahead and do an example of solving a difference equation. And the general form, really quickly, of YC of n for anything is going to be the summation k is equal to 1 to n C sub k times R sub k raised to the n. Okay, so if we only have one root, then we wouldn't have a second constant and a second root. We would just have this one thing. More often than not, this upper bound is usually going to be 2. Okay. Okay, so let's do an example now. So if I have a difference equation that's represented by, if I have a system that's represented by this difference equation, y of n is equal to 0.5 y of n minus 1 plus x of n. Okay. And in that system, I want to go ahead and input a signal x of n, which is equal to 2u of n. Okay. And assume that this system is causal. Okay. What is our output signal y of n? Okay. So the first thing we need to do is determine the particular solution. Okay. Well, if we look at our input, we have the form of a step function. So if we go back up to that table, for any form of a step function, our particular solution is simply just going to be some constant, C1. Okay. So that means our particular solution is simply C1. Okay. So now the next step is to plug that particular solution back into our difference equation. So we'll have C1 is equal to 0.5 C1 plus, and x of n is simply going to be 2. Okay. And the reason this time shift n minus 1 doesn't affect our particular solution is because if you think about it, if you have some like constant function here, it doesn't matter if we're at 0, if we're at 1, or if we're at -1, if we're at 2, it's always going to be that constant function. Okay. So that's why C1 never changes. So we have C1 is equal to 0.5 C1 plus our input. And the reason we don't use 2 U of n, we just use 2, is because since we're assuming causality, we know we're going to be at n is equal to 0 and above, so we can just go ahead and put that 2 there. So if we solve for this C1, we'll get, just subtract this over. Okay, then we'll get 0.5 C1 is equal to 2. So then C1 is equal to 4. Okay, so that means our particular solution is equal to 4 when n is greater than or equal to 0. Okay. So the next step now is to go ahead and solve for the characteristic solution. So to do that, the first step you do is set all your inputs to 0. Okay, we don't have to worry about that. So we would have y of n is equal to 0.5 y of n minus 1. Okay, we don't worry about the inputs. And we want to move everything to the same side. So we'll have y of n minus 0.5 y of n minus 1 is equal to 0. Okay. And now to determine the order of your characteristic equation, you simply look at the highest delay term. So for us, n minus 1, that means we're first order difference equation, okay? And so you would literally just kind of copy this over into the format we had of AR squared plus BR plus C. But since we're first order, we don't have this AR squared. We'll simply have R minus 0.5 is equal to 0. Okay. And it's kind of reverse of difference equations. The non-delay term is always going to be your highest order, and the subsequent delay terms after that will be the descending orders. So this will be your R, and this will be just your constant. Okay. So that means our root is equal to 0.5. Okay. So that means our characteristic solution, if we remember that general form, is going to be C2. And I'm going to say C2 because we've already used C1. So just to kind of stay consistent, I'm going to use C2 times 0.5, our root, raised to the n. Okay. And just for safekeeping, we always kind of say that this is multiplied by the step function to show that it's causal. Okay. And so now the next step is we need to solve for this C2. So to do that, first, we're going to say, I'm sorry, not that. We've got to do our full solution, y of n is equal to the particular solution plus the characteristic solution. Okay. So that's going to be 4 plus C2 times 0.5 raised to the n. Okay. And whenever I'm doing like actual algebra and stuff on these equations, I'll go ahead and get rid of that u of n because we're assuming n is always going to be greater than or equal to 0. But whenever you have your final answer, make sure to always include this u of n. Okay. And so now to solve for C2, what I need to do is basically establish my own initial condition since I didn't have that. So if I rewrite our difference equation, y of n is equal to 0.5 y of n minus 1 plus x of n. What I want to do is create my own initial condition. So the easiest one is always for n is equal to 0. So that means y of 0 is equal to 0.5 times y of negative 1 plus x of 0. Okay, all I did was plug n is equal to 0 into my difference equation. And so what this means is, remember, we're a causal system. So for any inputs where, or for any signals where n is less than 0, we automatically get an output of 0. So y of negative 1 doesn't exist. It's just 0. Okay. X of 0, if you remember, our x of n was 2u of n. And if you remember from u of n, it starts at n is equal to 0. And it continues on. So that means at x of 0, we do have a value, and that would simply be 2. Okay, so that means y of 0 is equal to 0 plus 2, which is just 2. Okay, so that establishes our initial condition. So we'll plug that in. We'll come back to this. So y of 0 is equal to 2, which is equal to 4 plus c2 times 0.5 raised to the 0. Okay, anything raised to 0 is just 1. So it's just 4 plus c2. Okay, and then if I subtract this 4 over, okay, that means c2 is equal to negative 2. So that means our total solution, y of n, is equal to 4 minus 2 times 0.5 raised to the n. Okay, and because we're a causal system, this whole thing is going to be multiplied by u of n. Okay, so that's our answer. Does anyone have any questions on that? No? Okay. I have another example from the sample exam y'all have. Would y'all like me to go over that? Just might take a while because it's a pretty long question, but it does mess with complex numbers. So if y'all want, I could go over that, or I could move on to the next example. What would y'all prefer?
I mean, sure.
Okay. Yeah, I'll go through it. Because it's definitely something you'll probably see on your test, messing with complex numbers. So we'll do a second example. So we have a system described by this difference equation. Y of n is equal to y of n minus 1 minus 0.5 y of n minus 2 plus x of n. Okay. The input signal we want to use is x of n is equal to 0.5 to the n u of n. And what is our output signal? Okay. So first things first, determine the particular solution. For this family of inputs, we'll have C1 times a to the n, okay? And in this case, our a is 0.5. So we'll have C1 times 0.5 raised to the n, okay? And I could put the u of n here, but I'm just going to assume that n is always greater than or equal to 0. Okay. So now let's plug this back into our difference equation. So C1 times 0.5 raised to the n is equal to C1 times 0.5 raised to the n minus 1. Okay. This time n is actually in our particular solution, so we do need to take into account these delays. Okay. Minus 0.5 times C1 times 0.5 raised to the n minus 2. Okay. And then our x of n is simply 0.5 to the n. Okay. So now we just need to do some algebra to basically solve for this C1. So every question you get regarding particular solution, it's always going to be different algebra steps to actually solve for your constants. You just kind of have to practice it and get used to looking at something and like, okay, what's the first thing I should do? So for in this case, the easiest thing to do since we have exponentials is to make sure that everything that has an exponential is all raised to the n. I want to try to get rid of these n minus 1s and n minus 2s. I want every exponential to be raised to just n. Okay? So the way we can do that is say C1 times 0.5 raised to the n is equal to C1. And I'm going to take out a 0.5 to the negative 1. And that leaves me with 0.5 raised to the n. Okay, does everyone see that? And then next, I'm going to do the same thing here. So I'm going to take this 0.5. So remember, this is just this part right here. Okay, I'm going to take out a 0.5 raised to the negative 2 so that I'm left with C1 times 0.5 raised to the n. Okay? And then this input stays the same, 0.5 raised to the n. All right? And so basically what this becomes is, if you've got a negative exponent, it just means you're dividing. So C1 divided by 0.5 times 0.5 raised to the n minus C1 times 0.5. Okay, so I'm just bringing these two over. And this 0.5 over to the negative 2 is simply 0.5 squared, but on the bottom. So that would just be divided by 0.25. Okay, 0.5 squared is just 0.25. And all of this times 0.5 raised to the n. And then lastly, 0.5 raised to the n. Okay. So the next thing is to do some simplification. Okay, 1 divided by 0.5 is simply 2, right? So that means I would have 2C1 times 0.5 raised to the n. Okay. 0.5 divided by 0.25 is also just 2. Okay, so minus 2 C1 0.5 raised to the n. Okay, plus 0.5 raised to the n. And all of this, remember, is equal to C1 times 0.5 raised to the n, this part right here. So now what we can do to isolate C1 and get rid of these exponentials is simply divide by 0.5 raised to the n. Okay. And that'll get rid of all of these, which will leave us with 2C1 minus 2C1 plus 1. Right, so there's a 1 here, which these will cancel out. So that means we're left with C1 is equal to 1. Okay, remember, we still have the C1 here. Okay, so our particular solution is equal to just 0.5 raised to the n, since our C1 was just 1. Okay, and this is for n is greater than or equal to 0. Okay, the next step is our characteristic solution. Okay, so I'm going to go ahead and copy this over. Maybe not. I'm really bad at this. Anyways, I think I remember it. I'm going to rewrite our difference equation, except we're using the characteristic solution. So I'm going to move everything over, okay? Okay, so for characteristic solution, remember, we just ignore the input term, and we move all the y terms over to the same side to set them all equal to 0. Okay, so y of n minus y of n minus 1 plus 0.5 y of n minus 2 is equal to 0. Okay, so now if we look here, we have an order of 2. Okay, and remember, it's opposite of differential equations. This is not your r squared term. This is your r squared term. So we'll have r squared minus r plus 0.5 is equal to 0. Normally when we look at an equation like this, we can easily factor it. More often than not, your roots are going to be complex. So just to save yourself some time, I would honestly just always use the quadratic formula. Saves you some headache of like, oh, why won't this factor? Okay. So if we do that, we've got b squared, which is just 1, plus or minus the square root of, negative b, plus or minus the square root of b squared, which is 1, minus 4 times a, 1, times c, 0.5, okay, divided by 2a, which is just 2 times 1, okay. So that will get us 1 plus or minus the square root of negative 1 over 2, okay. So that gives us 1 plus or minus 0.5j. All right. No, sorry. Plus or minus j over 2. Okay, and this just simplifies to 1/2 plus or minus 1/2 j, or if you want to write it in decimal, 0.5 plus or minus 0.5 j. Okay. So that means our R1 is 0.5 plus 0.5 j, and our R2, which is the conjugate, is 0.5 minus 0.5 j. All right. So now we can go ahead and write our characteristic general form, and it's going to be C1 times 0.5 plus 0.5 j raised to the n plus C2, which remember C2 is just the conjugate of C1, times 0.5 minus 0.5 j also raised to the n. And now we need to solve for C1 and C2, and because now we have two unknowns, or first we need to go ahead and put the entire equation together. So our particular solution was 0.5 raised to the n, okay, and now plus our characteristic solution. Plus 0.5 j raised to the n plus C2 0.5 minus 0.5 j raised to the n. Okay. Now we need to determine our own initial conditions, and we've got two unknowns. Okay, so we're going to need to make two initial conditions, one for n is equal to 0 and the other for n is equal to 1. So I'll rewrite my difference equation right here. Y of n is equal to y of n minus 1 minus 0.5 y of n minus 2 plus x of n. Okay, so for n is equal to 0, we'll have y of 0 is equal to y of negative 1 minus 0.5 y of negative 2 plus x of 0. So remember, we're causal, so these are for sure zeros. Okay, and x of 0 is, we go back up to our x term, we have 0.5 raised to the n, so anything raised to 0 power is just 1, right? So that'll be 1. So that means y of 0 is just 1. Okay. If we plug n is equal to 1 back into the difference equation, we'll have y of 1 is equal to y of 0 minus 0.5 y of minus 1 plus x of 1. Okay. And we're causal, so this y of negative 1 is 0. This y of 0, we already have that. It's 1. Okay. And this x of 1 is 0.5 raised to the 1, so it's just 0.5. So that means we have 1 plus 0.5, which is just 1.5. And those are our initial conditions. Okay. So now let's solve for our constants. So y of 0 is equal to 1, which is equal to 0.5 raised to the 0, right? Because n is equal to 0, plus C1, which, my bad guys, I should have used C2 and C3 to keep it consistent, but just know that from now on right now, C1 and C2, I'm just referring to the constants from the characteristic equation. But yeah, so we got C1 times 0.05, oops, 0.5 plus 0.5 j raised to 0 plus C2, 0.5 minus 0.5 j raised to 0. So that's just going to be 1 is equal to 1 plus C1 plus C2. Okay. For y of 1, that's equal to 1.5. We'll plug that in. I'm going to skip a few steps here. So 0.5 raised to the 1 is just 0.5. Plus C1 times 0.5 plus 0.5j raised to the 1. That stays the same. Plus C2 times 0.5 minus 0.5j raised to the 1. So that stays the same. Okay. So basically, this is our system of equations here. This is what we're going to use to solve for C1 and C2. You could go about this brute force method and just, you could do substitution or elimination. whichever one you want to do, but they're both very tedious because we're messing with complex numbers. Kind of a shortcut is to remember that when we have complex roots, our constants themselves are also complex. Okay, so that means C1 is of the form alpha plus beta j. Okay, and C2, remember, it's the conjugate of C1. So that means that's of the form alpha minus beta j. Okay, so we just look at this equation here. 1 is equal, and I'm going to move that over, 2. Okay, so I'll just move the 1 over here. 2 is equal to C1 plus C2. If I substitute these in, well, then I've got C1 is equal to alpha plus beta j, okay, plus alpha minus beta j. So these beta j's cancel out. So that means 2 is equal to 2 alpha. So alpha is simply equal to 1. Okay. Let me make sure I did that right. Oh, oops. I can't add, guys. Sorry. This is 0. So that means 0 is equal to 2 alpha. So alpha is equal to 0. Okay. That helps us because that basically tells us our C1 is only beta j, and our C2 is negative beta j, because we know that alpha is 0. So if we want to go ahead and basically plug these beta j's back into this equation, we can say that 1.5 is equal to 0.5 plus beta j times 0.5 plus 0.5j, okay, minus beta j times 0.5 minus 0.5j, okay. We just expand that out. I'm going to subtract this over, okay. So we've got 1 is equal to beta j times 0.5, okay. And then if I multiply this here, a j times a j is negative 1, okay. So then that would be minus beta 0.5, okay. And then we come over here, minus beta j times 0.5. And then lastly, we've got j times j, which is negative 1, but then we've also got negative times negative. So that'll go ahead and give us positive, okay? Or no. I'm sorry. That'll be negative times negative is positive. So it's just a positive 1 times a negative 1, which will continue to be negative. So we will get minus beta times 0.5. Okay. So these beta j's will cancel out. And we'll have this 1 is equal to minus beta. Okay. All right, I'm just adding these two together. Negative 0.5 minus 0.5 is just negative 1. So that means beta is equal to negative 1. Okay. So now we have beta is equal to negative 1 and we have alpha is equal to 0. That means we have our C1s and our C2s. Remember, C1 was just alpha plus beta j. So that means C1 is simply negative j. And C2 was alpha minus beta j. Okay. So C2 is just positive j. Okay. And to convert this to polar coordinates, negative j is simply e to the negative j pi halves, and j is e to the j pi halves. Okay. The reason that being is, if you look here, I mean, x is 1 and y is negative 1. Your magnitude is just going to be 1 squared plus 1 squared, square root of that. You'll just have, I'm sorry, 0 and 1. So you'll just have a magnitude of 1. Okay. And then the angle here, pi halves, just comes from the negative y-axis on the unit circle. But yeah, so these are your constants in polar form and rectangular form. Okay. So if we plug all of that back in, we'll just have y of n is equal to e to the minus j pi halves, okay, times 0.5 plus 0.5j raised to the n plus e to the j pi halves times 0.5 minus 0.5j raised to the n plus 0.5n, the particular solution. Okay, and all of this is going to be multiplied times our step function. Okay, and the solutions that y'all have for this sample exam, I know it converts this right here and this right here to polar coordinates, which is pretty easy to see. It's just 0.707 e to the j pi fourths, right? Because we'll just have 0.5 squared plus 0.5 squared in square root. That's going to be 0.707. That's our magnitude. And our phase is tangent inverse of 0.5 divided by 0.5, which is just tangent inverse of 1, which is pi fourths. Okay. Y'all solutions has us converting these to polar coordinates and then using a trig identity to simplify it into cosine, I think. I'm going to be honest, I'm not too sure how that happened. So if I were taking this test, I probably would just leave it here. Sorry, I can't help y'all on how he went from this to that trig identity, but yeah. Hopefully if y'all just leave it like this, y'all should be fine. Okay. Yeah, that's what I was trying to find is the listing of that, but I could not for the life of me. That's okay. Okay. Yeah. Okay. Yeah, and so there's one more thing about difference equations that we need to cover, and that's going to be, where you at? Right here. Okay. So remember we have this form, this general form of a difference equation. K is equal to 1 raised to the n. A sub k, let me rewrite that. A sub k y of n minus k plus the summation of k is equal to 0 to L b sub k x of n minus k. So we've got these upper limits, wow, L and n. Okay. That general form of characteristic solution that we've been using is only suitable when n is when L is less than n. Okay. But if L is even equal to n or greater than, we'll use the same characteristic solution but modified a bit. We'll have k equals 1 to n, c sub k, r sub k raised to the n. And basically what we'll do is add this sum of delta functions, okay? A sub k delta of n minus k. Okay, so whenever a is greater than or equal to n, we'll go about our characteristic solution as normal, but we also need to add this sum of delta functions, which we'll also need to find the constants for as well. Okay, so an example of that, pretty short, should be, yeah, this one. Yeah. Okay. So we will have example, we'll have y of n is equal to 0.5 y of n minus 1 plus x of n plus x of n minus 1. And our input is x of n is equal to n u of n. Okay? That looks good. So if we look here, we see our highest order is 1. So that means n is equal to 1. And our highest order for our input terms is 1. So L is equal to 1. So that means n is equal to L, meaning we're going to have these extra delta functions. Okay, and our upper term for that limit is simply L minus n. So for in this case, it's 1 minus 1, which is just 0. So we would have the summation of k is equal to 0 to 0, a sub k delta n minus k. Because it's just 0 to 0, the only thing we're going to have to add is a sub 0 and times delta n. Okay. If this L minus n was, say, a 1, then we would also have to have like a1 delta n minus 1. Okay. But we don't need that for this case. So let's go about this as usual. A particular solution, yp of n. From the table, nu of n, our particular solution is just c1 plus c2n. Okay. And then we'll go ahead and plug this back into our difference equation. Okay. So c1 plus c2n is equal to 0.5 times c1 plus c2 times n minus 1. Okay. Plus x of n is just going to be n. And then x of n minus 1 is n minus 1. Okay. And to do some simplification, c1 plus c2n is equal to 0.5 c1, okay, plus 0.5 c2n, okay, because we're also taking the 0.5 here and then distributing that here, okay, and then minus 0.5 c2, okay, and we got plus n minus 1, okay. So let's go ahead and start putting stuff together. We would do, and the trick to solving for these constants is basically putting this right-hand side in the form of a constant plus a constant times n. And if we do that, we can just equate these constants to that. So I'll show you how that works here. So we've got c1 plus c2n is equal to, if we take all the non-n terms and relate that to c1, so that'd be 0.5 c1 minus 0.5 c2, and then minus 1, okay, plus all the terms that have n's in them, okay, so it'd be 0.5 c2, and then plus 2, okay, because this right here is just 2n, right, and they're all multiplied by n. So if we multiply those back in, we got 0.5 c2 and then 2n there. The reason we want it to basically equate this right-hand side to look like this is because now we can say that c1 is equal to this part and c2 is equal to this part. You see how they look similar? So if we do that, we'll have c1 is equal to 0.5 c1 minus 0.5 c2 minus 1, and c2 is equal to 0.5 c2 plus 2. Okay, so now we just solve for our constants. So we would have 0.5 c2 is equal to 2. So c2 is equal to 4. And then we plug that c2 back in. So we'll have c1 is equal to 0.5 c1 minus 0.5 times 4. So that's just going to be minus 2 minus 1. Okay. And that will basically get us 0.5 c1 is equal to negative 3. So then c1 is equal to negative 6. All right. So cool. Now we've got our particular solution. That's equal to negative 6 plus 4n, for n is greater than or equal to 0. Okay. So now let's do our difference equation. Our characteristic y of n minus 0.5 y of n minus 1, just moving everything over, okay, is equal to 0. We disregard the x of n terms. So then we would have r minus 0.5 is equal to 0. So r is equal to 0.5. And remember, right now L is equal to n, so we need that extra delta term right there. So our characteristic solution would be, I'll use C3 times 0.5 raised to the n, but we don't stop there. We also need plus A0 times the delta function. Okay? And so for the total solution, we would have y of n is equal to minus 6 plus 4n plus C3 times 0.5 raised to the n plus A0 delta n. And what sucks about this L being greater than or equal to n, now it turned a pretty simple problem where we only had one unknown, and it turned it into a problem that has two unknowns, C3 and A0. Okay. So now we need to do the same thing that we always do, is go ahead and create our own initial conditions. So if I've got, we'll use n is equal to 0. So then plug it back into the difference equation. So y of 0 is equal to 0.5 y of negative 1, okay, plus x of 0 plus x of minus 1. Okay. And remember, x of n is just n u of n. So we're causal, so that's 0. This is also 0. It works the same for input terms. Okay. And x of 0, well, we will get an output, but because it's n u of n, and we plug 0 into there, we're still just going to get 0. Okay. So when n is 0, y of n is equal to 0. For n is equal to 1, we'll have y of 1 is equal to 0.5 y of 0 plus x of 1 plus x of 0. Okay. And so we determined that y of 0 is equal to 0, so this will be 0. X of 1 is just 1, right? So that's 1. And then x of 0 is, we determined it to be 0 also. So we'll just get 1 here. Okay. So now we've got our two initial conditions that we can use to go ahead and solve for our constants. So we'll have y of 0 is equal to 0, which is equal to minus 6, okay, plus 4 times 0, so that's just 0, plus C3 times 0.5 raised to 0, which is just 1, so we just have C3, okay, plus A sub 0 delta of 0, and delta of 0 is just 1, right? So we'll keep that A0 there. Okay, and then y of 1 is equal to 1, which is equal to minus 6 plus 4 times 1, which is just 4, plus C3 times 0.5 raised to the n, or raised to the 1, which is just 0.5, plus A0 times delta of 1. Remember, delta of 1 is just 0, so this whole term becomes 0. Delta is only 1 when n is equal to 0. So this helps because that got rid of one of our constants there, so we can just simply solve. So if we move everything over here, we'll have 7 minus 4, which is 3, equal to C3 times 0.5. So that means C3 is equal to 6. Plug that into this equation, and we'll get, we'll add the 6 over. So 6 is equal to 6 C3 plus A0. So that means A0 is equal to 0. Okay? So that means our total solution, now that we have our constants, is y of n is minus 6 plus 4n plus C3 raised to 0.5 raised to the n. And A0 is 0, so we don't even have to worry about that term anymore, which is quite annoying because now it seems kind of useless. But yeah, that would be our answer. Okay. Cool. So now the next topic that we have regarding solving difference equations using difference equations is the impulse response. Okay. So the impulse response is quite simple but very important. And we define this impulse response as h of n. That's what we'll call it. Okay. So what that means is if we have an impulse function delta n, we put it through a system, the response, we call it h of n. Okay. So remember, we're just putting a delta function through a system, and whatever the response may be, whether it's a decaying exponential, if it's a sinusoid, if it's a rising exponential, whatever it is, that's called h of n. Okay. The other term for this is called unit sample response. Okay. So this is a pretty important topic because we'll use it once we get to convolution. But basically, if you're going to solve a difference equation, if it asks you for what is the impulse response, what is h of n, using what we have been using before, the particular and characteristic solution. So, for example, we've got y of n is equal to y of n minus 1 minus 0.25 y of n minus 2 plus x of n. Okay. If it's asking, okay, go ahead and find the impulse response, that means right away, okay, we know we're finding the impulse response. That means we need to set our input function to the delta function, the impulse, right? Okay. And if you notice on that particular solution table, that delta function isn't there. Well, that's because the particular solution regarding a delta function is just equal to 0. So that means our total solution for an impulse response, so we're calling it h of n, right, is simply equal to the characteristic solution. Okay. And basically to solve for this, we're just going to go through the same steps that we have for the past three problems. Just instead, we're going to be using x of n is equal to delta n. And so our particular solution is equal to 0. So you would just solve your characteristic solution. And when you're going back to create your initial conditions, plugging your n is equal to 0 and equal 1 back into the difference equation, just remember that your x of n is delta. So for n is equal to 0, we'll have 1. For n is equal to 1, we'll have 0 for the x term. So yeah, let's see. I'll go ahead and do this example. I'll continue with this example. So we need to solve for our characteristics. So y of n minus y of n minus 1 plus 0.25 y of n minus 2 is equal to 0. So we'll get r squared minus r plus 0.25 is equal to 0. So that gives us r1 and r2 are both equal to 0.5. So we've got real repeated roots. So that means our solution, yc of n, is equal to c1 times 0.5 raised to the n plus c2n times 0.5 raised to the n. Okay? And now we need to find our initial condition. So we'll set n is equal to 0. So y of 0 is equal to y of minus 1 minus 0.25 y of negative 2 plus x of 0, which is just delta of 0, right? So these would be zeros, but delta of 0 is 1. Okay. And then y of 1 is equal to y of 0 minus 0.25 y of negative 1 plus x of 1, which is delta 1, okay, which delta 1 is 0, y of negative 1 is 0, and we determine y of 0 to be 1. So we'll have 1 here. Okay. So to find our constants, got y of 0 is equal to 1 is equal to c1 times 0.5, well, raised to the 0, so that's just c1, okay, plus c2 times n, which is also 0, so it's literally just c1 is equal to 1. And then y of 1 will have 1 is equal to c1 times 0.5 plus c2 times 0.5, because n is equal to 1. So we already have c1, so that's awesome. So that means we'll just have 1 is equal to 0.5 plus c2 0.5. So that'll simplify to 0.5 is equal to c2 0.5. So c2 is equal to 1. So that means our total solution is y of n is equal to 0.5 raised to the n plus n times 0.5 raised to the n, all times the step function. Whew. Okay, and finally that concludes difference equations. Okay. Any questions on difference equations? Good. Okay. And remember, this is going to be a long review because it's a long test. So if you do need to leave at any moment, feel free to. This will be recorded. We'll upload it to YouTube. So no harsh feelings there. But for those of you who do want to stay live, before we get to convolution, we can take like a quick 5-minute break real quick, get some water, walk around real quick. I'll be back because I got to get my computer charger. But yeah, I'll see you guys in 5 minutes. Okay, we're gonna go ahead and get started here now. Bear with me. We're almost there. We're almost there. Really quickly though, one thing I forgot to mention with impulse response, because this you'll find very useful, is we always end up going back to this general form of a difference equation. Okay. Okay. So this general form of a difference equation, there's actually different formats of it. This one in particular is called the ARMA format, which is referred to as the autoregressive moving average format. You don't really need to know why, but the reason it's important is because another form of a difference equation is if this entire term right here is equal to 0. So that would mean y of n is simply equal to the sum of k is equal to 0 to L b sub k x of n minus k. So this means y is only dependent on input terms. Okay, and this form is called MA, moving average. Okay, the reason this is important is because when trying to determine your impulse response, if you have a difference equation in the form of moving average, your impulse response is already there. It's super easy. Your impulse response is simply the coefficients of your input terms. So that would be B0, B1, B2, and so forth. Okay, all the way to Bn. If you want to look at an example would simply be y of n is equal to 2x of n, okay, minus 0.5 x of n minus 1 plus 3x of n minus 2. Okay, so here we have a difference equation in the moving average form because we only have input terms. We don't have any output terms in the difference equation. So that would mean our impulse response h of n is simply reading the coefficients. Okay, so our 0th term refers to x of n, our 1th term refers to x of n minus 1, our 2nd term refers to x of n minus 2. So it'd just be 2 minus 0.5 and then 3. Okay? So that's really important. So when a difference equation is represented in a moving average format, the impulse response h of n is simply the coefficients of the input terms. Okay, and that's pretty important. Okay, now we'll go ahead and start with convolution, which is our last topic. Okay, so up until now, this whole solving DT-LTI systems, it's all been the same thing. You know, we have an input term, we have a system represented by a difference equation. We need to find out what that output signal is. And we've been using the difference equation method, using characteristic and particular solution to solve that. That is such a difficult and annoying method. This whole class is going to be about figuring out different methods to do that, to solve a DT-LTI system. So the next method that y'all learned within the time domain, every other method is going to be the frequency domain, which you'll learn after your test. The next method in the time domain is called convolution. Okay, and convolution is actually quite simple, and it makes your life a whole lot easier than using particular and characteristic response. Okay, so convolution takes advantage of our LTI properties, linear and time invariance. Okay, so I'm going to kind of take you step by step of what exactly convolution is so you can have an intuitive understanding of it. So if we have just some impulse, right, we put it through a DT-LTI system, okay? we're going to get an impulse response out, right? Okay. And basically, if we're messing with the DT-LTI system, if we move this impulse, if we shift it by k, and we put it through the same system, we should get the same impulse response out, but also shifted by that amount k, right? Okay. Also, since the system is linear, if I multiply this delta function, I'm sorry, hold on, not x of n. If I multiply this delta function, delta n minus k, by some constant x of k, and the reason I'm saying x of k is constant, and the reason I'm using x of k instead of n, is because k can equal 0, it can equal 1, it can equal 2. We're actually putting a number into here, whereas n just represents a variable. Okay. So if I take this delayed impulse and I multiply it by some factor x of k, okay, because we're also still messing with the DT-LTI system, I should get the same impulse response, also delayed by the same amount, but also scaled by the same amount, x of k. Okay. So now I'm going to introduce you to something that will really help with the understanding of this class. Any signal x of n can basically be broken down into a summation of x of k, where x of k is a specific term of x of n for a specific n, times some delta functions. Okay? So if y'all remember, so let's say I have this function here. Okay? If y'all remember, if I took x of 0 and I multiplied it by the delta function, I single out x of 0, right? And if I take x of 1 and I multiply it by the delta function, shift it by 1, I basically sample this one part of the signal also, right? So basically what this is saying here is that any signal can actually be broken down into a sum of weighted impulses, samples. So these impulses are time shifted to basically sample this part of the signal. Okay, so what I mean by weighted impulses is these are all impulse functions, but they're weighted by these constants. Okay, and if I add all of these together, well, I get x of n. Okay, hopefully everyone can see that, right? I take x of 0 times the delta 0, and I sample right there. X of 1 times delta n minus 1, I sample right there. And for instance, n here is 1, n here is 2, and oops, n right here is 3. And so that's how I'm able to sample. Okay. So if we come back to deriving convolution, okay, well, if I've got any function x of n is equal to the sum k is equal to 0 to n, x of k, delta n minus k, okay. Which, by the way, for this, then that means the upper limit for this would be 3. So we can sum 4 times. But yeah, so if I put this now through a DT-LTI system, okay, what I should get is a summation from k is equal to 0 to n of x of k times h of n minus k, right? And this actually so happens to basically be, if I have an input x of n, and I know I can express it as the sum of weighted delayed impulses, and I know I'm going to get, basically, on the output side, I'm going to get the sum of weighted delayed impulse responses. Well, the same way I decomposed x of n into weighted delayed impulses, I can express my output y of n into a sum of delayed impulse responses. Okay? So to visualize that, if I've got some impulse and I put it through a DT-LTI system and I get some exponentially decreasing impulse response, okay, I'm going to shift this impulse over by 1. And let's say this is 1 because x of 0 is 1. And let's say here x of 1 is equal to 2. So now this is also weighted by that much. I'm going to get the same impulse response, but shifted over by 1. Okay? And it was multiplied by a factor of 2. And I'm going to keep doing that. And basically, if I keep adding these, I'll get x of n. And if I keep adding these impulse responses, I'll get y of n. That's all convolution is breaking down your input into a sum of weighted delayed impulses and breaking down your output into a sum of weighted delayed impulse responses. And so what convolution tells us is if we have the impulse response of a system, which is unique to every system, we can easily find the output, y of n. Okay? And the summation that I showed you, so y of n is equal to the sum of k is equal to 0 to n of x of k times h of n minus k. Okay? This right here is known as the convolution sum. Okay? Since we're in discrete time, we get lucky and we can use summations. In continuous time, you would have to use an integral, which could get really messy. And shorthand notation for this is y of n is equal to our input, whatever our input is, convolved, which that's what this symbol means, is convolution with the impulse response. And this is just a shorthand notation for this sum. Okay. So basically, if we want to determine the output of a system given a certain input, okay, as long as we know the impulse response of that system, we can easily find the output. Just do convolution. If we have the impulse response, just do convolution. We don't need to do characteristic in particular solution, just convolution. Okay. So let's go ahead and do an example. Okay. Let's look. Let's do this example. Yeah. So use convolution to find y of n when h of n is equal to 3, 2, 1. Okay. And x of n is equal to u of n minus u of n minus 3. Okay. And I hope that everyone can kind of start to see this already, that this is simply 1, 1, 1. Okay. Because we've got this step starting at 0, right? And basically subtracting this step that starts at 3. And that goes on. Okay. So all that leaves us with is this part, because everything else will get canceled. Okay. So now I'm going to introduce you to graphical convolution, which is how we'll solve this. Okay. So the steps to graphical convolution is time reverse h of k. Okay. And then we'll push h of k through x of k. and sum all the intersecting products. And you'll see what I mean by that. Okay. So let's come over here. So remember our h of n was 3, 2, 1, and our x of n was 1, 1, 1. Okay. So let me draw this graph. And let me draw x of n real quick. So that would be here 0, 1, 2. Just be 1, 1, and then 1. Okay. So this is x of n, but I'm going to call it x of k. Okay. Just to stay consistent with this sum. Y of n is equal to sum of k is equal to 0 to n x of k times h of n minus k. Okay. And now I'm going to completely time reverse h of n. So you think this is h of n. Okay. It's just a linear 3, 2, 1 going down. Okay. If I time reverse it, that means I'm flipping it about the y-axis. Okay. So that means here at 0, that 3 stays there. Okay. At -1, now I have 2. And at -2, I now have 1. Okay. So this is h of minus k. Okay. And now one thing to note is that the length a of h of n is 3, and the length b of x of n is also 3. So the length c of y of n after you do convolution is equal to a plus b minus 1. So for our instance, that would be 3 plus 3 minus 1, which is just equal to 5. Okay. So we know that for y of n, it's going to have a length of 5. Okay. So now let's start doing this. So basically, we're going to start with y of 0. Okay. And I'm going to show you how this graphical convolution relates to this sum pretty easily. So if we look here with graphical convolution, all we want to do is take the intersecting points, okay? And so in this case, our graph is only intersecting at n is equal to 0. We have 1 and we have 3 intersecting, right? So we're going to go ahead and multiply those. So we've got 1 times 3. And what we would do is if we have any other intersecting points, we would also sum those products. But this is the only intersecting point, so y of 0 is simply equal to 3. Okay? And in terms of the convolution sum, well, then that's simply k is equal to 0 to 0. Okay, it relates directly to that. So then we would have x of k times h of n minus k, which would simply be, if k is 0, we'll just have x of 0 times h of 0, right? N and k are both 0. And that's exactly what we have here, right? We've got 1 is x of 0, and 3 is h of 0, right? H of 0, 3, x of 0, 1. We multiplied those two together, and we got 3. Awesome. I'm going to circle that so we don't lose it. So now the next step is to literally push h of minus k through x of n. So x of n is going to stay stationary. Okay. So x of n never moves. X of n stays right here, 0, 1, 2. But h of n, we're going to start pushing it to the right. So that means 3 is now right here. Okay. 2 is now right here. And the 1 is right here at -1. Okay. So this right here is x of k, and this is now h of 1 minus k, because n is equal to 1, and here n is equal to 0. Okay, so we would have y of 1. Remember, just take the summation, the products, and sum them, the intersecting products. So we've got 1 times 2. Okay, right here. plus 1 times 3. So that's just equal to 5. Okay. In terms of the sum, we've got k is equal to 0 to 1 of x of k h of n minus k. So we would simply have x of 0 times h of, so this would be 1, okay? H of 1 plus x of 1 times h of 1. I'm sorry, times h of 0. Okay, 1 minus 1. And that's exactly what we have right here. X of 0, h of 1, x of 1, h of 0. Okay? So that's our second term. Remember, we need 5 terms. Okay. The next one, n. Leave x the same. And now we've pushed through this way, pushing one more to the right. And there's 2 1s here, right? I'm just going to label it as 1, 1. But remember, there's 2 1s overlapping right here. Okay? So now we've got y of 2. Okay, this is n is equal to 2. So we've got h of 2 minus k. And we've got x of k. Y of 2 is equal to 1 times 1, our intersecting points right here, plus our intersecting points here, 1 times 2, plus our intersecting points here, 1 times 3. Okay? So that's, of course, equal to 1 plus 2 plus 3, that's 6. Okay? In terms of the sum, k is equal to 0 to 2, right? We got x of k, h of 2 minus k. So that's going to give us x of 0 times h of 2 plus x of 1 times h of 1 plus x of 2 times h of 0. Okay? And that's what we've got exactly up here. Next, we'll have n is equal to 3. Okay? We'll draw x of n first, like I have been doing. 0, 1, 2. 1, 1, 1. Okay? And basically, we've got an intersecting 1 here. Okay? Then we've got 2 right here. And at n is equal to 3, we actually have 3. Okay? So we've got h of 3 minus k, and we have x of k. So y of 3 is equal to, remember, our intersecting parts. So 1 times 1 plus 1 times 2, which is just equal to 3. In terms of the sum, we'll have k is equal to 0 to 3. 3 minus k. And this will basically give us x of 0 times h of 3, which what you'll notice is h of 3 doesn't exist because h of n only is length of 2. So this whole thing is just equal to 0. Okay. Then we'll have x of 1 times h of 2 plus x of 2 times h of 1 plus x of 3 times h of 0. And same thing here, x of 3 doesn't exist because x is only of length 2. So this is also 0. And so that's why this graphical part only has 2 products, because these are basically 0. And that's kind of where the graphical convolution comes in handy, is you don't need to do all these tedious sums that end up equaling 0, because just by adding the intersecting points after you multiply them, that's all you need to do. And finally, our last term, n is equal to 4. We'll have 0, 1, 2, 3, 4. Okay. 1, 1, 1. That's x of k. And for h of 4 minus k, we'll have 3 right here, 2 right here. We're pushing it one more. and an intersecting 1 right there. Okay. So that means y of 4 is only equal to 1 times 1, right? Just this intersection right here. And that's equal to 1. In terms of the sum, just so I can finish it out. All right, we'll have k, h of 4 minus k. We'll have x of 0, h of 4, okay, plus x of 1, h of 3, plus x of 2, h of 2, plus x of 3, h of 1, plus x of 0, h of 4. And h of 4, x of 4, h of 0. H of 4 doesn't exist, h of 3 doesn't exist, okay? X of 3 doesn't exist, and x of 4 doesn't exist, so we just have this right here, okay? And so what that means is we finally finished our convolution. So y of n simply equal to 3, 5, 6, 3, and 1. Okay? So that's how you do convolution. You can do the sum this way, or you can do the graphical method. I definitely prefer the graphical method. Okay. And once again, just because you can kind of always get lost in the math when messing with this many stuff, let's always remember we're messing with signals. So we've got our input, x of n, right? It's just these 3 little ones. We put it through our system, and we knew the impulse response to the system, right? And what we got out was this y of n. We got 3, 5, 6, 3, and then 1. That was 0, 1, 2, 3, 4. Okay? Cool. Let's see. Yeah. So that's how you do convolution, either through the sum or the graphical method. Okay. I would definitely do the graphical method. I think on the test, this is how he did the sample one, which is actually my test from last semester, is he says use both the convolution sum and the graphical method. Well, if you're using the graphical method and you're just writing out your work, simply 1 times 2 plus 1 times 3 is equal to 5, you're doing the sum at the same time. So
some of them he did.
yeah, for sure. And that's why I'm saying I would use the graphical method, just because by using the graphical method, if you just write out your work, you're automatically using the sum. You're just choosing to lose out to exclude the product terms that equal to 0. Okay. And to be safe, I would always draw your output as well. Okay. We're almost there. The next topic is convolution properties. Okay. Convolution has a ton of properties. Some very self-explanatory ones are associative. So, x of n convolved with h of n is equal to h of n convolved with x of n. We got associative properties. You also have distributive properties, which I'll get into here in a bit. But one of the main ones that you'll need to know is time shift. Okay, and that's simply if we have x of n minus a, and we convolve it with an h of n minus b, so they're both being time shifted by different amounts, okay? Then we will get y of n minus a minus b, okay? So the time shift of the output kind of sums, okay? But the big one is convolution with an impulse. Okay? So the way this works is if we have x of n, and we convolve it with some impulse that's delayed by a amount, the result of this convolution is simply equal to our original x of n function delayed by that same amount, x of n minus a. So if x of n, if we convolve it with a delta function that's time shifted by no amount, so just n, we would simply get x of n out. Okay, it stays the same. If we take x of n, we convolve it by an impulse that's delayed by 1, well, what we get out is just x of n minus 1. Okay. And I'm going to relate this to the distributive property. It's pretty simple. We can just distribute. So if we have x of n and we want to convolve with, say, like delta n plus delta n minus 1 plus delta n minus 2, okay, we can actually distribute this. But remember, our convolve with impulse property. So this would give us x of n times delta, or convolved with delta n, which is just x of n. And then x of n convolved with delta n minus 1, which is x of n minus 1. And then x of n convolved with delta n minus 2, which is just x of n minus 2. Okay. Cool. And now the reason the impulse property is so important is because with convolution, we used the summation and we used the graphical method. There's actually a third way that'll come in handy at some point called convolution using delayed impulses. Okay, so all this means, and I'm going to use the same example. If we have x of n, and it is equal to 1, 1, 1, and we have h of n, which is equal to 3, 2, 1. Okay. Remember, we can always break apart a function into a sum of delayed impulses. So I can say that x of n is simply equal to the coefficients times delayed impulses. So all these coefficients still happen to be 1, so it's pretty simple. Delta n plus delta n minus 1 plus delta n minus 2, right? And if, say, this was 2, we would just have a 2 right here. But they're all 1, so it makes our life a bit easier. And remember, y of n is equal to x of n convolved with h of n, okay? And remember, associative property, so we can actually have h of n convolved with x of n. It's the same thing. So if we actually write that out, we'll have h of n convolved with our x of n, which we rewrote as delta n plus delta n minus 1 plus delta n minus 2, okay? And we can do the same thing we did above. We just distribute everything and use the convolution with impulse property. So that would mean that y of n is equal to h of n, right? Because we're just convolving h of n with delta n, plus h of n convolved with delta n minus 1, so that's just h of n minus 1, plus h of n convolved with delta n minus 2, so h of n minus 2. So convolution actually using delayed impulse responses. Okay, so this is key right here, is that we can just express our convolution as a sum of delayed impulse responses. So if we do want to use the same thing, that would mean y of 0, okay, I'll just do the convolution really quickly, is equal to h of 0 plus h of minus 1 plus h of negative 2, which is just equal to, remember these are zeros, so it's just equal to 3. Y of 1 is equal to now h of 1 plus h of 0 plus h of minus 1 So that's 0. Okay. And then this was 3. And this is 2. Right? So then we get 5. H of 2 is equal to h of 2 plus h of 1 plus h of 0. Okay. So that's going to be h of 2 is 1, right? So we got 1 plus 5. That's what we determined. I'm sorry, no. Plus 2, and then plus 3. So it's 6. And then h of 3 is equal to h of 3 plus h of 2 plus h of 1. H of 3 doesn't exist, so then we'll just have h of 2, which is 3, plus h of 1, which is 2. So we got 5. And then the final term, we'll have h of 4 is equal to h of 4 plus h of 3 plus h of 2. These don't exist. This is just 3. So we got 3. Okay. And when you use this delayed impulse response method, you need to know the length of your convolution. Okay. And remember, that's just C is equal to A plus B minus 1. And so using this delayed impulse response, we were able to get our convolution in a much, much faster way. Okay. So there's a tip. Okay. Finally, we're on to the last topic of this review, which will be covered on this test. And that's going to be series and parallel systems. Okay. So, what is a parallel system? A parallel system is simply we take one input, and this input is split between two systems. Okay. And it produces a single output. So this dotted line is our total system. Okay. And so we could say the individual outputs of these systems are y2 of n and y1 of n. With parallel systems, so this is parallel. Okay, this total response, y of n, okay, you simply add the two. Y of n is equal to y1 of n plus y2 of n. Okay? So an example of that is if we have, basically, we have an impulse response of one system, h1 of n, is equal to, same thing, 3, 2, 1. Okay? And we have another system, and its impulse response is 1, 2, and 3. Okay? These systems are in parallel. What is the total system impulse response? We'll call that whole impulse response simply h of n. Okay? So that means we've got a delta, okay, an impulse. We put it through two systems. This will be h1 of n. This will be h2 of n. And the notation I'm using here is, like I said before, impulse responses are characteristic of a system. They're unique to them. So a notation that a lot of people like to use is the naming their systems their impulse response. So they'll actually put the naming impulse response h1 of n inside of that block system. Okay. And I'm trying to find h of n. So h of n is simply equal to the sum of h1 of n plus h2 of n, which is then equal to 3, 2, 1 plus 1, 2, 3. So h of n is equal to, if we add them, we'll get 4, 4, and 4. And there's our zeroth term. Okay? So that's parallel systems. They're really easy. A more complex system is a system in series. So if we have a function or a signal x of n, we put it through a system, okay? And we take that output of the system and put it through another system, we get an output, okay? And here's the total system, okay? So I'll consider this y1 of n. And I know it looks weird, but really, this is y2 of n. This isn't, y2 of n is not the same thing as y of n. Y2 of n is simply the response of this system by itself without this other system in series, okay? So when you have a series system like this, y of n is equal to y1 of n convolved with y2 of n, okay? And if I had multiple systems in series, you know, it would keep going all the way to n of n, I guess. I guess I'd rather call this k. Okay, and that's the same thing with here. Okay, with parallel systems, I could say this goes all the way to yk of n. Okay, however many systems you have in parallel or systems in series. Okay, so now let's do an example. Here we go. Since this one's a bit more difficult, I think I would do maybe 2 examples. We'll see. Okay, let's do an example. So we have a system x of n. A signal x of n. We put it through a system with the impulse response h1 of n. Okay. We put that response through a system with the impulse response h2 of n. We want to know what the total impulse response is of the system, the full system, the total system, okay? So what is h of n? Okay, and h1 of n is given as 1 and negative 0.5, okay? h2 of n is also given, but not directly exactly. Or I'm sorry, no, h2 of n is not given. Neither is h1 of n. I misled y'all. They give us the difference equations of the systems, okay? So the difference equation modeling this system right here is y of n is equal to x of n minus 0.5 x of n minus 1. The difference equation modeling this system is y of n is equal to 0.5 y of n minus 1 plus x of n. Okay. So now I need to determine h1 of n and h2 of n so that I can convolve them to get the total h of n. Okay, h1 of n is super easy to get because remember, if you look here, this is in moving average form. It's only input terms. When it's only input terms, remember the impulse response, you just read the coefficients. So we got 1 as our 0th term, and we have negative 0.5. Okay. Now h2 of n is a bit trickier to get. If you notice here, we have an output term, meaning we're in the ARMA format. We're not in moving average. So we need to go ahead and do something we haven't done in a while using difference equations. Okay. So how do we do that? Remember, when finding an impulse response using a difference equation, the particular solution is simply equal to 0. So that means our impulse response, in this case h2 of n, is equal to yc of n. Okay, so let's do the characteristic for this. So we got y of n minus 0.5 y of n minus 1 is equal to 0. Okay, so the characteristic equation is r minus 0.5 is equal to 0. So r is equal to 0.5. So then yc of n is equal to c1 times 0.5 raised to the n. Okay. And of course, times u of n. But now we need to figure out c1. So we use n is equal to 0, and we'll plug it back into the difference equation. So y of 0 is equal to 0.5 y of negative 1 plus x of 0. Remember, this is an impulse response, so our x is a delta function, so we have delta 0. And y of negative 1 is just 0 because we're causal, and delta of 0 is 1. So our y of 0 is equal to 1. Okay? So now let's solve for c1. So yc of n is equal to 1, which is equal to c1 times 0.5 raised to the n. I'm sorry. 0. Okay. And so this is to the 0th power, so this is just 1. So that means c1 is equal to 1. So our h2 of n, which was equal to yc of n, is equal to 0.5 raised to the n u of n. Okay? So what does this tell us? Our h1 of n was 1 and negative 0.5. So we have 1 here and negative 0.5 here. So 0, that's 1. This is h1 of n. Okay. Our h2 of n is a decaying exponential. Okay. It starts at, let me scale this better. It starts at 1 and it decays from there. Okay. This is h2 of n. We need to convolve these. Okay. Because h of n is equal to h1 of n convolved with h2 of n. Okay. We could do graphical, but why do that? Especially because, this exponential, although it gets infinitesimally small, it still never fully converges to 0, right? It never quite reaches that 0. It goes on infinitely. But we can go ahead and use one of our convolution properties. We can represent h1 of n, which was equal to 1 and negative 0.5, as a sum of delayed impulses. So delta n minus 0.5 delta n minus 1. Okay? And we can say h of n is equal to the convolution of h1 or h2 of n, which is 0.5 raised to the n. Okay? And I'm going to go ahead and use the full thing now, 0.5 raised to the n u of n. Okay? Convolved with delta n minus 0.5 times delta n minus 1. Okay. So remember the property, we convolve them with an impulse, we just change the time shift. So convolving this whole thing with an impulse, it remains the same. 0.5 raised to the n times u of n. Okay? Minus 0.5 times 0.5 to the n minus 1, right? Because we're convolving with an impulse that's delayed by n minus 1, times u of n minus 1. Okay? So you could honestly leave it at here, but to simplify it further, I'm going to go ahead and take out 0.5 raised to the n u of n. 0.5. I'm going to take out this 0.5 to the negative 1 to leave me, which is 0.5 to the n. So that cancels out. So I've got this, right? 0.5 raised to the n u of n minus 0.5 to the n u of n minus 1. And hopefully y'all can see this without graphing it, but I'm going to graph it just so you can visually see it. This right here is just a decreasing exponential starting at 0. And it starts at 1, right? The 0.5 raised to the 0 is just 1. Okay. This right here is also a decreasing exponential, but it's delayed by 1 time unit. Okay. So instead of starting at 0, it starts at 1, but the magnitude still starts at 1. Okay. And we're basically subtracting these two. And let me see this real quick. Oh, I'm sorry. No, this starts at 0.5. Okay. The reason it starts at 0.5 is because even though at n is equal to 0, we have 1. At n equals 0 here, we have u of -1, so we have a value of 0. Okay. So then once we hit n is equal to 1, this value right here will be 0.5, and we'll also have u of 0, so we can go ahead and start the decaying exponential. And this second value here is also 0.5. So if we subtract these two, this whole thing gets wiped out by this, leaving us with just this delta function right here. So this whole thing is actually just equal to delta n. Okay, I think y'all would be fine leaving it here, but I just wanted to kind of show y'all how if you change it to a graph format, you can see that these graphs actually cancel each other out for the most part, except for that delta. But yeah, that should be everything that is covered on y'all's test. Okay. So that's everything I have in terms of material. If there's anything you guys want to discuss or have any questions, feel free to let me know right now. If not, the recording should be up hopefully tonight, if not tomorrow. And I'll also go ahead and save this OneNote document, and I'll go ahead and post it in the Discord so you'll have access to that too. Okay. But yeah, do y'all guys have any questions or comments? Okay, cool. If there's nothing else, I'm done. I won't be too available this weekend, but if you really, really need help before the test on Monday, please feel free to reach out to me. I'll see if I can figure something out. But yeah, thank you guys for staying the whole time. I'll see you guys later.